All right, fair warning, there is calculus in this problem. You don't see a lot of it in mechanics and materials, but this time, yes. Because when you have objects hanging downwards, weight is like a distributed load. The very bottom of it has almost no weight hanging beneath it, and each little bit up you go, you get more and more weight. Since weight changes continuously, right? The amount of force pulling downwards changes continuously as you go up and up this pipe, right? The amount of stress is going to change throughout the entire pipe here. That means calculus. Whenever forces are changing continuously, that's calculus. So let's find the maximum stress in each pipe and the total amount of stretch. If we have, right, these thousands of feet of pipe hanging down from the surface, right, how much total will they be stretched? And you can just stare into your Indy's face over here on camera B. All right, so let's work from the bottom up to the top. Because down at the bottom, at point D, there's no stress there at all because there's nothing beneath it. There's no force pulling at D. So stress at D is going to be 0. So for CD, that bottom pipe, the maximum stress will occur at point C, which is supporting the entire weight of all the pipe down beneath it. So stress is force divided by area. So if we have a total weight of 2 pounds per foot times 2,000 feet, that's the total amount of force. That's the total weight of the pipe divided by the surface area of the pipe. We get 3,200 pounds per square inch, or 3.2 KSI. Moving up to pipe BC, we have, again, at point C, there's only CD weight beneath it. But at point B, we have the total weight of both pipes hanging, so the max stress on that middle pipe will occur at the very top, which has the maximum amount of weight beneath it. That total amount of weight will be the 4,000 pounds from pipe CD plus the 2.8 pounds per foot times 5,000 feet, the weight of pipe BC. All right, a little bit of calculator work. Max stress in pipe BC, 10.3 KSI. We'll repeat this one more time now for A to B. Again, stress at A will be more than stress at B because A is carrying more weight. And that amount of weight is going to be the 4,000 pounds from the bottom pipe, the 14,000 pounds from middle pipe, so 18,000 pounds below point B, plus the weight of the top pipe AB, which is going to be that 3.2 pounds per foot times 5,000 feet, which adds another 16,000 pounds. Stress works out to be 13.6 KSI. Normally, axial load is going to be calculated NL over AE. This is when you have point loads or loads connected to walls. So this is just a summation when you have stretching in tension or compression. This problem is an exception. It's going to be an integral of NL over AE because the distributed load amount N is changing over length. At the very bottom of the pipe, there's no weight pulling. And as you keep increasing in height closer to the surface, you have more and more weight. So N keeps getting larger and larger. So you're doing an integral and the variable being changed, like your boundaries of integration, are your length. So the first integral is going to go from 0 to 2,000. And the N term here is going to be the 2.0 pounds per feet. And our length is X, right? That's the dx, that's the variable we're distributing over, length. So instead of L, I'm writing this as X. In the denominator, area was given, but E, I'm going to have to look up in a table. A36 steel, going to be 29 times 10 to the 6. Second integral for the middle section of pipe, integrating from 0 to 5,000, where now the weight is going to be 4,000 plus 2.8 x. So for example, at 1,000 feet into the pipe, the total amount of weight beneath it would be 4,000 plus 2.8 times 1,000. So 6,800 is the amount of weight that would be below that point. We go up to 7,000 feet, and there'd be 4,000 plus 2.8 times 2,000. So an extra 56. So 9,600 pounds would be below that point. So 4,000 plus 2.8x is n, the normal force in this case. Third integral is going to look similar, also a 5,000 foot length, but this time the forcing equation n, 18,000 for the total weight of the bottom two pipes, plus the 3.2x for the amount of weight being added for every additional pound in that third section. And just reinforcing that we're still doing NL over AE, right? N is the amount of weight, right? The 18,000 plus 3.2x. L is dx, right? Once we integrate from 0 to 5,000, this dx term essentially becomes length, right? This is each unit of length. And then A in the denominator and E also in the denominator. So refresher from Cal 1, the integral of x is 1/2 x squared. The integral of 5x, right, is 1/2 5x squared. That coefficient in this case, instead of 5, is 2 divided by the area and also divided by the e. So my coefficient in this first integral is 5.5 times 10 to the minus 8, right? 2 divided by area times e. So 1/2 times that n over AE times x squared, and we are doing this from 0 up to 2,000. So the 0 will basically cancel out, and we can just plug 2,000 in for x. And that works out to be 0.1103, and my units here are in feet, because all of my dimensions here, 0 to 2,000 feet. The second integral is going to be kind of the same, but a little bit different, because now in the numerator, there's 4,000 plus 2.8x. So I actually have two different terms here. The 4,000 divided by AE is a standalone sort of separate term, separate from the 2.8x. So again, just to go back to the calc review, the function x plus 3, the integral of x plus 3 is 1/2 x squared plus 3x, right? The x becomes an x squared term. The number by itself, the coefficient, ends up in x term, So my 2.8x term is going to lead to a 1/2 x squared, but my 4,000 term is just going to be that 4,000 divided by 1.75 divided by the 29 times x. Of course, there's going to be a giant negative coefficients here because I'm dividing by this 29 times 10 to the 6. But plug all this in, do some calculator work. 0.6875 for this middle integral. So that's 2/3 of a foot. This is about 8 inches. This middle section is going to be stretched. And the third integral is going to be pretty much just like the second one. Again, there's a constant term, the 18,000, and then an x term, the 3.2x. So the constant term, we're just going to take the 18,000 divided by a and e, and then just put an x next to it. And the 3.2x also has to get divided by a and e, but then it becomes a 1/2 x squared term. So when we plug in 5,000 for x, we get 0.55 feet is the amount stretched from the x squared term. So that's based on the weight from A to B alone. And then 1.24 feet from the x term. So that's the amount of stretch that happens just from the pipes beneath it, like from BC and CD. So when you combine these, you can see that this is almost 2 feet of stretch. That this 5,000 foot pipe, based on the weight of all 3 pipes pulling down on it, stretches almost 2 feet in that top section. And in fact, when we add up all 3 integrals, all the total lengths, 2.98 feet. So this giant massive pipe hanging down gets almost 3 feet longer just based on its own weight acting as a distributed load to cause it to stretch out. If you learned something from this video and you want to do me a quick tiny little favor, hit the subscribe button. I know it's a vanity metric but I still love seeing the numbers tick up just a little bit every day. So thank you so much. Have a great rest of your day, great weekend, and good luck on your next test.